ready.
Okay, super.
Okay, and I've just activated the subtitles. Can you see them all right?
Ah, wow, super, yes.
It's automatic. I'm not doing anything. So sometimes it makes some silly text, but at least it's a bit better than nothing. So thank you so much for having me today. And thanks, Alessandra, for the introduction. So I'm going to talk in this talk first about what we think can make a good data set. So in neuroimaging, we often work with a lot of data. So a little bit of reflection coming out of neuroimaging on what is important for a data set and how this impacts on our results and how this opens up a discussion for neuroimaging brain sciences in general. Then I will go through different examples of standards and tools that can help us share more than just research papers. And then finally, because I think this is really important, and that's basically the title of my talk here, I will discuss different initiatives to take part in the open science community, which is for me the most exciting part of open science, really. So let's get started. So yeah, here we are. So on this chart that comes from a paper that was published in 2017, you can see median sample sizes as a function of time going from the mid-1990s up to 2015. Mid-1990s is nice because it's the beginning-ish of functional MRI, which is a technique that is used quite a lot in brain sciences. And when we look at this chart that was produced by Bodrak and colleague, you can see the first thing we see is that there is a trend, like sample sizes are increasing, meaning that per study, we are inviting more and more participants. But if we look more closely at the last point on this curve that corresponds to 2015, we can see that the median sample size was of 30 participants. And well, 30 is I think still considered small sample size, and now we're going to discuss why that could be an issue. And the speakers before me have already covered that, so I'm going to cover some complementary aspects. So using an example, as I was saying, that doesn't come from the neuroimaging community. So here's an article that was published in the Atlantic Science in 2019. And the title is "A Waste of 1,000 Research Papers." So what do they mean by that? Basically, the article, which is a press article, is covering a paper that tried and reproduced a study in genetics using a bigger sample size, and basically the results didn't replicate. And because the original paper was quite of a landmark paper, a lot of literature had been built onto it, and basically making the point that these results were in fact probably not true, had a strong impact on the literature. So that's one of the issues we can observe when we have small samples. Another effect that we have to take into account is the idea of vibration effects. So we've touched a little bit upon with the previous talk about the researchers' degrees of freedom. The idea that when you do an analysis, there is not just one single way of doing it, but there are probably a couple of alternatives that would be considered equivalently valid. Those alternatives, if we try them out, if we try them all, leads to different results. And this is what we call the vibration effect. The fact that the results that we obtain are not just one, but there can be a family of results. And we know that as the sample sizes are smaller, that vibration is even stronger. So this is one issue of small data set. Then I also really like that study that came. So this was an analysis done by using data from a running app. So I'm not a runner myself, but I see a lot of people just like going out with their phone. They have this app, and then they come back and the app tells them how far they run, how long they've run, and so on. And so they used the data from different users in this app to compare how fast people who were in their 20s run compared to people who were in their 40s. And what the study showed is that basically people who were in their 40s run faster. And that doesn't make much sense. Like there were discussion around, but probably we could agree that people in their 20s should run faster. And so one possible explanation that they give in the article is that basically the data set, the way the data set was acquired by looking at the data from this app had a selection bias. So basically people who were in their 20s that used that app, we had all type of runners. So you had beginners, you had people who were like going to run every 3 days, you have people who wanted to run a marathon. You had a very heterogeneous group. On the other hand, when they looked more closely at the population of people who were in their 40s and used this app, they only had a group of much more experienced people. And basically, when comparing the runners in their 20s and the runners in their 40s, they were comparing groups with different level of experience. And that was created this artifactual difference, saying that runners in their 40s would run faster than runners in their 20s. Now here's a third example of when the data set can cause issue, and I've taken these examples because it was published just a few days ago on July 5th, and this one is about a speech recognition system. So very much like the one I'm using right now, you can see that sometimes these systems make mistakes. And what is shown in that paper is that, what is discussed in that article is that basically these systems will make more errors when they try and recognize the speech from people who have accents, for instance. And this has also been shown in other studies. So on facial recognition systems as well, it was shown that they worked better, they worked not as well for women and people of colors. And this is most probably due to the fact that the system were trained on data sets that weren't diverse enough. They weren't representing the population as a whole. So lack of diversity is also a big issue for data sets. So going back to neuroimaging research, we've mentioned our 30 participants. What we really want to achieve is to build bigger data sets that are more representative of the population and more diverse. And this leads to my second section. So we've discussed data sets in the fact that we would like to make them bigger and better and more representative. And as was discussed in the 2 previous talks, the community in neuroimaging, but in other data science community as well, researchers have realized that point, that we have to build bigger data set. And one obvious way to do that, the first starting point can be just to make sure that we pool our data together so that we can work with bigger data sets. So here I'm going to discuss publishing research artifacts beyond papers. So here on the left, you have a typical pipeline that you could use in brain science. So here I've used task-based fMRI as an example, but really these could apply to, well, any data science type of pipeline. So we start with some raw data. We have a pre-processing phase that I sometimes call feature extraction. The idea is to clean up the data. So in neuroimaging, that could be, for instance, a random motion correction algorithm, do a segmentation on the anatomical images, and so on. And then you get some derived data that you think are relevant to study the question you are interested in. And finally, we compute a statistical analysis. If you're more of a machine learning person, that could be a machine learning algorithm, and we get some results. And the way the research community is working is that typically we are going to write a paper. And we've touched upon this a little bit, but being at an open science workshop, I can only recommend that the paper, beyond publishing it in a highly prestigious journal, you make it available as well on a preprint server, on a postprint server. In my institution in France at INRIA, I have to put all of my papers on an institutional archive once they are published. So it's not preprinting, it's postprinting. Okay, so that's one thing. We share a research paper, but we said we want to achieve this bigger data sets. So one thing researchers have started to do is to package their raw data, make a nice puzzle. That's what I've tried and illustrate here. And but the question is, how can we build that puzzle? Because basically, we want to share brain images or brain signals, but we also, for those to be really reusable, we also have to like share information about those. Let's say you share a couple of images. How do you know which images belong to which subject? How do you know specific characteristics of your files? So for instance, in functional MRI, you might want to have information about slice timing of the acquisition of your images, and so on. So there are many pieces of information that we refer to as metadata that are really important, and we need to share with the data for the data to be reusable. And we've mentioned, I know it was mentioned this morning in the chat, I think that BIDS is a very nice standard right now that has been well accepted by the community to package raw data and make sure that these metadata come along with it. So I'm not going to discuss BIDS because luckily there is a talk tomorrow by Guillermo Arniso who will cover a BIDS. So I don't want to give many details, but I think this is quite a well-established standard right now. And what is really nice is that they've built extensions. So beyond MRI, where it all started, now MEG, IEEG, EEG, and so on are starting to get into that framework, which is really a community effort. Oops. So we've discussed packaging our data with BIDS, which is probably the best standard available right now. And once we have that package, well, there are a number of homes, databases where we can go and put that data. So an obvious example is the former fMRI, now Open Neuro, but there is also XNAT Central, Loris has a version, Chat Noir, and so on. So many different places where those data can be uploaded and made available to the world. Now, sharing raw data is nice, but basically our research paper also includes some data. So I'm referring to task-based fMRI here. Typically, we have these tables that summarize the results where we have the X, Y, Z coordinates of the locations that were corresponded to the highest statistic values, and those are available into tables. So some databases are focused on making sure that those data are available in machine readable form, either via crowdsourcing with like the community converting the tables into that program, or by having like staff who are dedicated to doing that transformation. So that's one great thing. But beyond that, if we go one step earlier, like before we had the paper, our results over here are themselves data. And similarly to what we've done with raw data, we could package that results data and make it available, and that would open up new use for other researchers. So here, I take the example of a task-based fMRI results. So typically what we have in a publication to display the actual results, we have figures that are 2D because the publications, the way they are built right now, must be printable. So we have 2D slices. The way we select the slice is going to change what the researchers who is reading our paper understand of these like locations in the brain. We have that table I've already talked about, and we could in fact convert that table into an image that would be super sparse with just these peak location with a statistical value if these were shared. So of course, this is incomplete, so we don't have the statistical values everywhere in the brain being reported, which is against good statistical practices where every time you do a test, you should basically share the output of the test, whether it was significant or not. We can have incomplete methods, so I think this is widespread. In journals, we only have so much space to share our methods, so it's really nice to get a high-level overview, but that doesn't provide like the level of details we might want. And of course, this is a PDF, so metadata is not searchable. It's not meant to be machine readable. So a few years back, in 2016, I worked with a group of researchers on NIDM-Results, which is a standard to share task-based fMRI results. So what you get is an archive, a zip archive, in which you have a number of images that, as a group, we decided were important when we report about fMRI results. So for instance, you will have the statistic image with values everywhere in the brain. You will have the thresholded image in totality rather than just selected slices, but also additional information. For instance, the design matrix, which often is really important if you want to understand what actually was going on in that study. And there is one extra file that includes a lot of metadata about the whole analysis. So I'm not going to list all of them, but to take just one example, for instance, in there, you have the contrast that was used to build the fMRI statistics. And this is quite important if you want to do meta-analysis later on, because using, for instance, a 1-1 contrast will lead to the same statistics as a 2-2 contrast. But if you look at the contrast map themselves, they will have different units, which change the way we can combine them into meta-analysis. So those pieces of information are extremely important if we want to enable different data reuse. So NIDM-Results is implemented in SPM, and there is a tool for FSL. So those of you who are SPM user will recognize the interface here. So within the interface, there is the option to export the results as an NIDM, and you will get that zip archive we talked about earlier. There's a command line tool for FSL, and NeuroVault, which is that database that accepts statistic maps in fMRI. So also accepts NIDM. So basically, when you go on NeuroVault, you can just upload your Nifty file, and I think a lot of people do that, and NeuroVault will accept them, but you could equivalently upload an NIDM archive, and then NeuroVault is going to retrieve all the images that are inside, as well as the metadata that is so important. I've touched upon a little bit briefly on meta-analysis. So what is nice when we share more data, the more data we share, the more usage we open basically for the rest of the research community. And within NIDM-Results, one of the first use cases is that instead of doing coordinate-based meta-analysis. So a meta-analysis is just a new analysis that reuse the results from previous studies. So let's say there were in the literature 10 studies that looked at a specific aspect that you are interested in. Well, you can, with the meta-analysis, quantitatively summarize all the studies and see if there is evidence for activation, let's say, in one area of the brain. The way meta-analyses are done right now is by combining the P coordinates, because that's the only information we share in papers. But if we start sharing a bit more than that, using NeuroVault, using an NIDM, then we can achieve image-based meta-analysis, where we are going to combine data in every places of the brain. And you have an example here at the bottom. So on the left, the coordinate-based meta-analysis, and on the right, the image-based meta-analysis. And as we can expect, we get much more details with the image-based meta-analysis, because simply there was less data loss in the whole process. So we've discussed sharing raw data at one end. We've discussed sharing results data for one specific example. But what we haven't really discussed is what's in the middle here. So basically, there is a lot of data at that stage, and here I've only put the derived data, but basically we are producing large amount of data at every steps of our pipeline. How can we share those? Is this useful? And how can we share those? To the best of my knowledge, like, there is no single answer to this problem right now. BIDS is working slowly into that space with BIDS derivative, looking at like specific types of derivatives. As you can imagine, this space is just huge. And NIDM is also going in that direction, and I'll tell you a bit more about this later on. But that leads me to another aspect that I would really like to discuss before going any further. It's the idea that if we want to work with open data, we are going to have to deal with analytic variability. And I'll discuss now what I mean by that. So we've mentioned how researchers can share data using different tools and standards. And we are lucky right now in brain sciences that there is quite a lot of open data now being available. So the use case we've discussed until now was sharing data at, let's say, the end of a study. So you have your unique study. I've put 30 participants here because we've seen it's the median, but of course it could be less or more. And you can go and upload your data at the end of the study. I've also added here two examples, two more slightly different examples, which are study for rest and micronectome, that were studies where there were a limited number of subjects, but that were built to be shared with the community. So that's a different framework where rather than publishing my results and then sharing raw data, I'm basically building a resource to be shared with the community. So on that end of the spectrum, we have a lot of data that is shared, which is extremely heterogeneous, looking at different population, asking different research questions, and looking at different type of images. At some point, after that first effort of saying, as a researcher, I can share my data, researchers just decided that they would gather into subgroups or consortium to try and define a common goal about sharing data. So I think a very good early example of this is the 1000 functional connectome project, which looked at resting state fMRI data. I think resting state is really nice because there are challenges with acquiring this data, but you don't have the issue that you have with task-based fMRI, that you have to share the timing of your paradigm. And this was done at a time where bits was not, did not exist yet. So there was like no clear way how this could be done. So I think resting state fMRI was a great example, and the 1000 functional connectome project is one of those first efforts where people just gathered together, said, we want to have more resting state fMRI data and share it between lab and make it available to the rest of the community. And that's where there is a change in the order of magnitude of the sample sizes. We go from 30 participants to about 1,000 participants. Now, even more recently, we've seen funders getting really interested into building large data sets for the community, because just like us as researchers, they are aware that we need big sample sizes if we want to answer the complex questions we are interested in. Two obvious examples here for me are the Human Connectome project and the UK Biobank. The target of UK Biobank for the imaging data only is to have 100,000 participants. So it's a big change in the order of magnitude. So on this like small chart, you see many different ways data is shared in our community. On one end, we have a lot of small data sets, really heterogeneous, looking at many different things. On the other hand, with cohort imaging, you have data sets that are really big, but there are only a few of them. They are extremely homogeneous, and then this means that they also are limited in the scope that they are covering. So now, how all of these open data can impact the way we do our analysis. So going back to our analysis pipeline. So again, I have my raw data, some feature extraction or pre-processing, however we want to call them. We get derived data and we do a statistical analysis and we get our results. So that's historically how studies were done, and this leads to a very homogeneous pipeline. Like everything basically from data acquisition to the results could be done within a single lab. Now, if I want to work with open data, the first one of the use case that we already discussed is the possibility to do a meta-analysis. So I could go and find all the results that were shared in the literature and combine them with my results and see whether there is evidence of activation if we look at fMRI. So that's one way we can use open data. We also talked about open data being shared as raw data. So one thing I could do is go and find, and this is not always easy, but go and find some data that is similar to mine and inject it at the level of feature extraction. But because these data were acquired probably in a different settings than the one I have locally, it might well be possible that these data have to run through another feature extraction pipeline. And instead, I might have to combine this data at the level of the statistical analysis. And here, that means that I'm basically combining data sets that were pre-processed using different pipelines. Another example here would be the case in which I don't have access to the raw data. Let's say only the pre-processed data was shared openly. Why could that be the case? I think the first example, the first reason might be data privacy. So we know that in some cases, sharing derived results leads to less possibilities of re-identification. So sharing only derived data might be a way to ensure more data privacy for our participants. Another important reason, I think, is sustainability. So let's think again about the UK Biobank. We are targeting 100,000 participants. Does it make sense that every lab in the world go and redo their own pre-processing with their favorite pipeline? I don't think so. So if we are serious about using open data, at some point we are going to have to deal with a new level of variability, which is the what I've called earlier the analytical variability. And that level of variability comes from the fact that the data that we pull together have been partially analyzed using a different pipeline. So it could be a different pre-processing pipeline. If we are combining data at the level of statistical analysis, it could be a completely different pipeline from pre-processing to statistical analysis if we do a meta-analysis. Of course, there are other level of variations like change in scanners, in acquisition sites, and so on. But that analytic variability is something new when we combine this open data. So just to be a bit more specific about what might change from one pipeline to the other. So we said, okay, data sets could have been analyzed with the different pipelines. So what does this mean? I really like this quote from Karp's paper in 2012, talking about different acceptable analysis methods. So here is a couple of examples we could think about. On the left, you have what we'll call a canonical pipeline. That's the pipeline I've selected for that particular study. Well, the first alternative we can think about is to run that same pipeline where we're going to change the parameters of the pre-processing. And often, all these steps we have in the pre-processing, you could change a few parameters and that would be considered equivalently valid. Second alternative, I could use the very same pipeline, but change two algorithms. So let's say for segmentation, I use SPM new segment instead of the old segment. That would probably be considered equivalently valid. The third alternative is the same pipeline, but I use a different software version. And what's interesting is that if you look at the third circle on that third alternative, you see that we had to change the parameters as well because changing the version made the parameters different for some reason. Fourth alternative, run the same pipeline in a different environment. So let's say I run my pre-processing on a high performance cluster, and then I bring back the results to do the statistical analysis. And last alternative is the same pipeline using a different software. So think for task-based fMRI, SPM, FSL, AFNI. And by using a different neuroimaging software, probably some of the algorithms are going to be different because all algorithms are not implemented in all neuroimaging software. So this creates a family of pipelines that we would consider equivalently valid. And I think a very important question here is, well, how does this actually impact our results? And I'm not going to talk about this because there is a talk later this afternoon by Rotem Botvinnik-Nether. I'm really excited to hear about this great project that looked exactly into that. Like, if we give researchers the same data set and we ask them to answer the same questions, how valuable are going to be the results given that we leave them the choice of the analytic pipeline? So looking forward to this afternoon. But going back to our notion of like standards and tools, my dream in the future is that I'm going to be able to like get data from someone based in the US that pre-process their data using a specific pipeline, get data from someone else in China, let's say, that pre-process them using another pipeline, and that we will have tools that will read information about the pipeline and tell us this data is compatible or not with the pipeline I want to use locally, or maybe it's not compatible as such, but if you run that specific tool on them, then we can recalibrate the data and make it compatible, and then you can pull all of them together. So that's my dream. I can't wait for that to happen. But in order to be able to do that, we need to have that level of details about what happens at each and every step. Because right now, it's not very clear how each step impacts on the results. And so this is an effort that is called BEATS Provenance, which I'm currently doing with Satra Ghosh from MIT and Remy Adam, who's with me at INRIA. And we want to extend BEATS to describe provenance. So what we mean by provenance is really a description of that pipeline. What were the different steps? What were the parameters? Which neuroimaging software was used, and so on. This is an official BEP, so BEATS extension proposal, meaning that we are actually working on this, and we are very much looking for contributors, community input. If you're interested in like provenance, please join us. If you're not interested in provenance, but you'd be interested to know if the pipeline you're using can be correctly described with that standard, that's also something would be very interesting to hear. So please get in touch if that's the case. My email will be shared at the end of this presentation. So there are a number of efforts that let us share data right now, and there are a number of efforts that are going on. And what's I really like about defining standards is that these really have to be community effort. Like, it doesn't make sense for one group somewhere to define their own standards by themselves. And this brings me to my last section. Working together as a community. To me, I've mentioned it as an introduction, but I'm going to say this again because I think it's so important. The most important aspect of open science, we've talked about technical details, and that's my research background. But I think it's really the idea that we can work together as a community, we can learn together as a community. And I want to here describe a few initiatives that are international and open for contributors. And I know they would love to have you people here today attending this workshop who are interested in open science and in learning more. Of course, I'm biased from what I've personally lived, so I'm going to share how I personally interacted with this, but if you're interested, I'd be more than happy to say more about these open communities and how you can get involved. So the first community I got involved with is the INCF. INCF stands for International Neuroinformatics Coordinating Facility. So this was very much related to my work on brain imaging standards. So when I started as a postdoc at the University of Warwick, for the first time, I got to work with like a group of international researchers who were trying to define a format to enable more data sharing. And that's where we've developed NIDM-Results. One of these meetings was also where we discussed for the first time having something like BITS. So these, I think, are very important because, as I was saying earlier, the only way we can build standards is by gathering people from different places with very different views on things so that those standards are meaningful to many people. INCF right now has a very nice process to suggest a working group. So I would highly recommend that you look at the existing working group, join the one you're interested in, or if there is a topic that you would like to discuss with other researchers, that's also a nice place to get visibility and make sure that you have a group that is recognized and can be known by the community. So this is INCF and their working groups. Now, really quickly, when I was in my postdoc, I got to attend a brain hackathon. And for those of you who have not attended hackathon yet, I can highly recommend it. So hackathons are these conferences type of conferences or workshop where participants come and they decide which project they want to work on. So a few people in the assembly are going to say, I'd be really interested in looking in that tool or that or discussing that aspect of research and how it impacts the way I work. And then you have groups that just self-organize and work together. This sounds really unstructured, and first time I've been there, I was just like, what this is about? Like, where are the projects? But after one day, like seeing it unfold, I've realized that to me, this is a very nice setup in which you can see people working together, asking questions, saying, okay, I'm stuck on my analysis because I don't know how to do that. And then you would have someone else in the room just say, oh, I've already done that. Actually, you need to do this and this. And these are details, important details that we don't often discuss in conferences because we show that very polished version of our work where everything is finished. The hackathon is the contrary. You can go there and say, I'd be interested in working in that. It's not even the question might not be very polished, and then hearing feedback from people saying, hey, I tried that, didn't work, or did you know about this work that might be related to what you want to do, and so on. So a very nice space, and I want to give a shout out to brain hackathons, because those that we see in the brain imaging community, I really love how they frame it. So these are hackathons for collaborations, not competitions, which is quite different from the type of hackathon you might see in industry, for example, where people work together, do crazy hours and try to focus on one goal. Here it's much more like a widespread discussions around groups. So 2 more examples and then I'm done. The next thing I attended, and I can highly recommend it as well, is the Mozilla Open Leaders training. So they don't exist anymore as Mozilla Open Leaders, but they have subgroups that were created out of it and focus on different aspects of science and beyond. So this is a training. The way it works is that it runs for 12 weeks. Every other week you meet with a mentor, and the week you don't meet with the mentor, you have a full cohort call, so a Zoom call, just like the one we are having here, where there is a training about how to build, like the simple thing, how to write a README so that you can welcome collaborators. But to me, like working with the Mozilla community was the first time I could see practical ways to make our work more open by design rather than by default, making sure that we put the right things in place so that the community is more welcoming and people can meaningfully contribute. So I highly recommend that. And then to finish, so Alessandra earlier mentioned that this year I was the chair of the OHBM Open Science Special Interest Group, SIG for short. So OHBM is the Organization of Human Brain Mapping. They have one conference, international congress each year. And this working group on open science is organizing 2 main events. So the first one is a hackathon, a brain hackathon, just the one I discussed. It happens before the main meeting. So I'm talking about the event that happened this year, and I really want to thank Remigo and Lisa Levetis, who were the 2 persons really leading that effort of the hackathon. And we also have another event, which is called the Open Science Room, that runs at the same time as the main meeting. And this year, the event was co-led by Casgood Van Prague and Stephanie Innes. Stephanie is giving a talk a bit later in the workshop as well. These spaces are first places where you might want to go as an attendee, but these groups are also groups where you can take more of an active role into making open science growing in our communities. So this is a quick sum up of what happened this year. So both events run around 3 hubs in order to cover different time zones. For the hackathon, for instance, it was very important that people could work together at times that were that worked with their biological rhythm during working hours rather than in the middle of the night. And here's the map of the people who attended. Just like I really liked Vittorio's introduction at the beginning, saying that virtual events gives us an opportunity to reach out to a more global community, but there is still a lot of work for us to do. We have this responsibility to reach out to a more global community. And that's something I know the Open Science SIG is really looking forward to do this year. So I'll do a quick plug here. Nominations are open for the Open Science SIG. So if you're interested in taking a more active role in shaping open science, I can highly recommend this opportunity. There are a number of roles. Some of them are for 3 years. Some of them are just for 1 year, so that people, for instance, PhD student who might not want to spend a full 3 years can join and be there for 1 year. And I would be really happy to talk more about this if that's of interest. So before I finish, I really want to thank, of course, my team here in Rennes. I want to say a few words about and say thank you to Christian Barillot, who left us really recently. He was one of the person who pushed me into doing a PhD, and I will always be grateful for that. I had the chance to meet many people around my open science journey. A few of them are here. It's not an exhaustive list, and this is really important. It has shaped the way I do research. I've also added the 2 links to all the volunteers who helped with the Open Science Room and the hackathon this year, because those were really community efforts, and it's really important that we thank them now. Thank you so much for your attention, and I'd be really happy to answer any questions.
Thank you very much, Camille, for this interesting presentation. Are there questions from the audience? Just wait. Carlo Minucci starts with the first question.
Thank you, Camille, for the very nice presentation. I got a very general question. Since you presented that data on MRI, I'm wondering if was known as GDPR, so the General Data Protection Regulation, it's going to be a problem for data science, because those regulations will be valid for Europe, for example, but not for other countries. And so how can we share our data with other countries or vice versa?
So I'm really, really happy that you're asking this question, actually, because I think a lot of like open science efforts, at least the one I've seen in the past, have been led by North America, right? Like, for instance, Open Euro is hosted in North America, and this is one of the most widespread database for task-based fMRI. And to me, it's still not entirely clear how we can do how we can build open data, make it more widespread in Europe. And I know some groups are doing it successfully, but as you said, we have different regulations, and we have to understand how they work and how open data is possible within that framework. And now I'm going to point to Stefan Stog, Stefan Yunis. I think it's this afternoon, but I'm not so sure, where he will talk exactly about data sharing and privacy. And I know they've done some work into how we can make data sharing compatible with GDPR.
Thank you.
Thank you. Camille? Yeah, sorry, I lost you. Can I ask you another question? Which is the role of time in analytical variability? So I think when you acquire like 100,000 subjects, you have also upgrade from a hardware point of view. So is this relevant or not really?
So you mean upgrade in the software that you're
in the software, in the machine also?
Yeah, I think that's extremely relevant. So the thing about analytical variability right now for me is that we have a very bad understanding of how it really affects our results. Like, for instance, just what you say, like a change in version of one software happen all the time. And that's a nightmare when you want to do reproducible research, because you want to be able to say in your paper, I use that version. And then you start your analysis and the version change, and what do? You rerun everything, or you say you use two different versions. That's difficult. And I think it's even more difficult right now because we don't understand if that's important or not. Like maybe changing a version, like let's say a version of AFNI will not affect the specific tool you're using, and you shouldn't even worry about it. And that's why I'm very excited about the work Rotem is presenting, because that's defining in a setup where people are using the pipeline they use in the wild, what's the extent of variation. But I think we need more work into knowing whether changing software, changing machines, changing MRI is going to affect our results.
Thank you. Are there other questions? Okay, if not, I think we can thank Camille for your presentation. Thank you very much. And Carlo, I don't know if you want to add something.
Yeah, sorry, just take advantage of this situation, this meeting, to make a call to all Italian attending this conference, because the idea could be to launch an Italian chapter group to promote open science at national level. So the idea is not to create a new association. In Italy, as many of you might know, there is already an Italian association for promotion of open science, and University of Trento is part of that association, and Giulia De Reda is actually attending this meeting from the law department, is also part of that association. So the idea here is just to increase interest in this subject in the field of researchers that are actually studying the brain. And so if you want to contribute, you think you might give a contribution to this kind of approach, just send an email to this address, thinkopen.cimec@unitn.it, and eventually we will contact you if something will start. I think there's another question from Nicola Megna.
Exactly. So Camille, there's another question for you if you're still available.
Yeah, of course.
So Nicola Megna?
Should I read it?
I don't know. Yes, sorry. I can read it. I'm sorry. Are there similar resources in the field of psychophysics, like data sharing, results sharing, sorry?
So I'm unfortunately probably not the best person to answer that question, but maybe someone will add something in the chat. Sorry.
I don't see any further. So Massimo Grassi.
Thank you.
Can reply. Wait. Open the microphone. Massimo?
Okay, sorry. In psychophysics, there is not much. So, for example, a couple of years ago, we had an attempt of asking the Acoustical Society of America, which is the society I know, to launch, for example, registered report or some open science initiatives, and the response was really cold. In the sense that they were not interested. I suppose the field is kind of feeling very self-confident. We are producing very robust science, and we don't need so much transparency. And also last year in Rotterdam, at the International, the Society for Improvement of Open, SIPS, Society for Improvement of Psychological Science, sorry, in Rotterdam. I think the psychophysicist group was made of, we were 5 or 6. I don't remember, we had a lunch together. We are building up a group in a sense, but we are definitely a small community.
Maybe Julia, do I want to, Julia, share the link for the Italian association? Do you want to add something on that, Julia?
Oh, sorry. I was trying to unmute myself. Well, I just posted the link to the association, and we'd really love to have people interested in our project. And as I was saying, with regard to the previous talk, we are very interested in scientists that would like to receive legal training, and scientists who really are aware of all the difficulties from the legal point of view that they are facing, and they need help to deal with. I think that us as lawyers really should help the scientific community to deal with these legal challenges that usually, for those who are not experts in the field, are sometimes so big, so giant, that they feel they will not be able to really succeed in their open science dream or even a small project. So whenever you'd like to get in touch with us, you can use the link that I provided. There are email addresses over there, or you can also email myself. So I can post here my email address in case you want to contact me to chat over or perhaps to ask questions. And also the one of the president of the association, who is Professor Roberto Caso. So yeah, that's all.
Okay. Thank you very much. I think Vittorio wanted to add something. Vittorio Iacovella?
I think there's also a question from Gabriele Amorosino.
I may leave the floor to other questions before intervening. So I think it's one by Guiomar
Miso.
And another one by Gabriele Amorosino.
Who is Guiomar? Let me unmute.
Hi.
Yeah.
Hi. Hi. Thanks, Camille, for the super nice talk. I was going to ask you if can NIDM somehow be related to electrophysiological techniques like MEG or EEG, or is it just MRI focused?
So thanks, Guillermo. So NIDM as a concept is not just MRI focused, but then the question is like which models are implemented right now, and the main model that is implemented is the one I presented earlier about task-based fMRI results. There are a number of efforts looking at other aspects, not just MRI, but they are not completely finished yet, so it's work in progress. I personally think that really what NIDM should do right now is work hand in hand with BITS, and that's what I presented with BITS Provenance. The idea is really to have something that will let these two things work together, the best of both worlds, hopefully.
Yeah, I'm looking forward to the Provenance extension. Yeah. Okay, thank you very much, Camille. Thank you.
Thank you.
And then there is another question from Gabriele Amorosino. Let's see if we can unmute. Gabriele? I see his microphone is on, but maybe I can read his question for you. So the question is there a way to verify how abstract the derived data is from the original data? and therefore there is the possibility of sharing it without running into privacy problems. Gabriele, we cannot hear you, but I've read your questions.
Thanks for that question. I think that's a really nice one. So I think one of the things Beats Provenance could enable is exactly that. Sorry, making sure that we can point to the original data and then have a description of all these steps that were done and then point to the results data. And about sharing it without running into privacy problems. So I don't know if that's exactly what you meant, but what I'd really like to discuss is that with an NIDM, you have a possibility to share the metadata without the data. And that's very interesting in terms of privacy, because you might be able to say, we have a data set, it has these characteristics, and then you can access it later on. So you could like imagine making the metadata public and then giving access to the data only on a case-by-case basis, or once people have signed like data user agreements and so on.
Okay, thank you very much. Okay. If there are no further questions, I think we can really conclude this section.